Hello, let's see you again. And I'm inviting all of you for our lecture number 7. Uh, 1 second, please. And now let's start. Today we will be continuing our topics called fly-by-wire flight control. As we mentioned in previous lecture, modern FBW flight control system means fly-by-wire flight control system are implemented using digital technology. Signals being transmitted as serial digital data using time division multiplex data bus network. The signal data are subsequently processed by digital microprocessor in the flight control computer, which carry out the following tasks: voting, monitoring, and consolidation, control law implementation, reconfiguration in the event of failure, and built-in test and monitoring. Primary flight-by-wire flight control system using analog computing technology are still in service. But nowadays, analog technology is mainly used to provide a dissimilarly redundant backup system for protection from common mode failures, as just explained. The advantages of modern digital implementation compared with analog are overwhelming with the technology now available. For instance, hardware economy. In this case, one computer can control all 3 axes of control, whereas an analog system requires dedicated hardware for each axis of control. I hope you agree with this statement, right? Okay, and the reduction in hardware weight and volume is of the order of 5 to 1 for a system of even modest complexity. The more complex systems could not be implemented economically using analog technology. Flexibility, in this case, control laws and gearings or canes can be changed by software changes as opposed to hardware modifications, giving greater flexibility during the design and development phase. The introduction of modifications in service is also easier. The cost of software changes is not a trivial one, to say the least, but there is no doubt that it is still less than the cost of hardware modification. Reduced nuisance disconnect. Digital computation allows sophisticated voting and consolidation algorithms to be used, which minimize nuisance trip outs or simply disconnect. Smaller failure transient, sophisticated consolidation algorithm can be implemented, which minimize the transient experience on disconnecting a failed channel. But in test capability, very comprehensive self-test capabilities can be incorporated into the system for pre-flight checkout and maintenance. Digital databases, very large reduction in the weight of cabling are achieved by the use of the multiplex data transmission and data bus network. High integrity data transmission can be achieved with very comprehensive self-checking and data validation capability. The use of 3 or more totally independent data bus networks enable that failure survival requirements to be met. And this slide illustrates a flight control data bus configuration. The use of digital data introduces particular problems which need to be taken into account in a closed loop digital control system. And these are essentially due to the need to sample data and the frequency of sampling. And this diagram illustrates the effect of sampling a time-varying signal at too low a sampling frequency. The sample output contains a much lower frequency signal, which is not present in the real signal. The effect of sampling is to fold back the high frequency content of the real signal above the sampling frequency, so that it appears in the frequency range below the sampling frequency. Please see this diagram. And this effect is known as aliasing. Okay? It is thus necessary to filter the signal to attenuate any noise with a frequency content above the sampling frequency before sampling. Such filters are known as anti-aliasing filters. Let's see this diagram. And clearly, the higher the sampling frequency, the better, so that the lag introduced by the anti-aliasing filter is very small over the range of control frequency. Okay? Nice. Let's go on. In comparing the corresponding outputs of, say, 4 independent parallel computing channels or lanes, it is possible for the output of one channel to be delayed by 1 iteration period before its output can be compared with the other. Its information is thus stale by 1 iteration period. And hence, if the output quantity is changing during the iteration period, the output of this stale channel will differ from the others, also no fault has occurred. The situation is illustrated in this slide. To overcome this problem, it is necessary to have some form of time synchronization of the computer iteration period. This iteration period synchronization is generally implemented through software. The alternative is to allow longer iteration periods so that all computers are processing the same data. And this, however, introduces a latency or time delay in the output, which results in a phase lag and is destabilizing. And this figure illustrates the phase lag introduced by a time delay. Okay? And this results in a phase lag in the output, which increases as the frequency of the input increases. Look at this slide. Yes? Agree? Nice. The amplitude, however, is not attenuated, as with a simple lag filter, and so the destabilizing effect is increased. Software generation is one of the most challenging tasks in the design of a high-integrity digital fly-by-wire flight control system, and can account for between 60 to 70% of the total engineering development cost of the complete FBW system. And this is because of the size of the software which is required to carry out all the flight control functions and the problems of establishing the safety of the software. The main functions that are carried out by the software for the flight control computers can be delivered into three basic areas, which have a degree of interaction and comprise. It's three: redundancy management, control loss, and built-in tests. Redundancy management can account for between 60 to 70% of the total software. In the case of a modern civil F/W aircraft, the proportion is generally not quite so high. In a military FBW aircraft, it's around 50% for a model agile fighter. Implementation of the flight control laws generally accounts for between 25 to 30% of the total software in a modern civil FBW aircraft. The proportion in a modern agile fighter, however, can amount to can amount to around 40%. Built-in test software for in-flight monitoring accounts for a smaller percentage of the total software, in either case, around about 10%. However, during the pre-flight checking stage on the ground, the proportion of the operating software taken up by built-in tests is much higher and can be as high as 40%. Some appreciations of the functions carried out by the redundancy management software can be gained by considering the tasks involved in failure detection and isolation and reconfiguration in the event of a failure in case of quadruplex system with 4 independent lanes of sensor and computer. And this includes tasks such as sensor data validation, checking the digital data from each individual sensor is correctly encoded and has not been corrupted with the data transmission system. Sensor failure detection of a failed sensor by cross comparison of sensor data and majority voting. Sensor failure isolation and system reconfiguration. Isolation of a failed sensor and system reconfiguration to survive the failure and also to minimize the resulting transit. Sensor consolidation. Consolidation of the data from a group of sensors to use a single representative value for subsequent computation of the control law. In first order list of sensors for a typical system is set out in this table to show the numbers of sensors involved in these respective tasks. Most of these sensors would be at quadruplex or triplex level redundancy. Cross-lane data transfer. Data transfer between the individual computing lanes to enable cross-comparison of output, computer output voting and consolidation, cross-comparison of individual computer outputs to detect and isolate a computer failure, consolidation of the good computer outputs to provide the control surface demand signals to transmit to the control surface actuator sensor. Computer iteration period synchronization. The iteration periods of the individual computers need to be loosely synchronized to avoid data tailless problems. Recording of all data to enable the management of the maintenance function. System status indication to the crew and control of the overall system. Considering the considering the large number of sensors involved, plus all the other tasks described, enable some appreciation to be obtained of the redundancy management software tasks. The safety critical name of this software can be appreciated. The processes involved in carrying out just one of the sensor failure detection and output consolidation tasks is shown in the flow diagram in this figure. The control law software is, of course, of an equally critical nature, together with the built-in test software. The control laws now being implemented in the new generation of flight control systems are of much greater complexity than in existing conventional aircraft. The high-speed microprocessors now available enable very sophisticated control laws to be implemented and the aircraft to have a higher performance and safer handling characteristics as a result. The control law software is thus of increased complexity. However, the cost of generating this software also significant and can be amortized over the production round of what is a more competitive aircraft and hence can be cost effective. This is because the hardware costs are sustainably unchanged from earlier systems because of the continuing progress in processor power and microcircuit design and certainly manufacturing technology, such as the extensive use of ASICs, application-specific integrated circuits. The control law software tasks can comprise complex gain scheduling of many control types as a function of high airspeed, incidence, and possibly altitude aircraft configuration. This can be particularly important in a military aircraft, which may be required to operate to the very edges of its flight envelope in combat, when increased cross-coupling effect, etc., require changes in control terms to be made. The control transfer functions involve proportional, derivative, and integral terms, which must be derived from the various motion sensors using suitable algorithms, like automatic limiting of the pilot's input commands to achieve carefree maneuvering, to restrict the pilot from attempting to maneuver the aircraft into an unacceptable altitude or approach to near the stall or exceed the structural limits of the aircraft, or changing the control laws to maintain effective control in the event of sensor failure, or control of the secondary control surfaces, leading edge flaps, slats, trailing edge flaps, and spoilers, for control of engine thrust and possibly thrust vectoring. Another subtopic to the lecture, active fly-by-wire interceptor. The spring and tamper elements of a passive interceptor have been replaced by computer-controlled force feedback actuators on each axis. Algorithms within the controller provide the required force displacement characteristics by means of algorithms based on measured force and displacement in each axis. The active interceptor can produce the characteristics shown in this figure, with such features as variable force gradient with intermediate soft stops. Soft stops are intermediate force thresholds to bound the zone of carefree handling, while the variable gradient provides the desired field characteristics over the flight envelope. Provision of such characteristics in a passive interceptor would be impractical because of the mechanical complexity involved, right? With a digitally implemented controller, it is a relatively simple task to modify the force displacement characteristics of the inceptor during flight test without any mechanical changes to the unit. In addition to the ability to vary the field characteristics of the interceptor, it is also a simple task to provide such features as variable null positions to provide parallel trim and autopilot backdrive, or facilities such as the stick pushes or stick staker to provide cues to the pilot relating to buffet onset or imminent stall or departure. The ability to couple together the displacement of a pair of interceptors. It is this last facility which is seen as the major benefit of active interceptors compared with their passive counterpart. It is particularly relevant to train an aircraft, where the student pilot can detect on his interceptor small forces and movements from his instructor's interceptor. Simple logic with the respective controllers allows the instructor to override the student should it prove necessary. In transport aircraft, both the pilot and co-pilot are fully aware of each other's actions, much in the same way as with mechanically coupled traditional control wheel and pedestal, without the complexity entailed with mechanical crossfeeds. Finally, the operating concept of active interceptors does not just apply to the primary pitch roll control system in an aircraft, or the so-called pitch roll cyclic in a helicopter. It can also be applied to rudder pedal, throttle controls, and helicopter collective pitch control or collective level. And this figure shows the basic concept of a force-coupled pair of interceptors for a dual control system. Active interceptors can be made relatively small and compact. However, this is not always the case. Both the Boeing 777 and 787 have a F/W flight control system, but retain the traditional control yokes, which are coupled to a active intercept. The flight-by-wire control loss and the active force field system give these aircraft very similar handling characteristics to other Boeing airliners with conventional mechanically signal control. And this enables pilots to make a relatively easy transition between the Boeing airliners in the airline operators fleet. There are both active force or displacement interceptors and active force interceptors, but space constraints limit coverage to the more common force or displacement type. And this figure is a schematic diagram of an active displacement type of fly-by-wire interceptor. Here, brushless DC servo motors are shown as providing the actuating force. Okay? And the gear drive reducing the power required. Brushless DC servo motors are chosen because of their excellent torque characteristics and reliability. Very effective damping can be provided by the inherent electromechanical damping in the DC servo motor, amplified by the feedback within the servo amplifier. Consider what happens. Sorry. Consider what happens when the pilot exerts a gentle pressure on the stick to displace it from the normal central position. This force is sensed by the force sensor, and the stick force or displacement controller generates zero stick displacement demand at this point, as it is below the brake outlet. The servo motor force balances the force the pilot is applying, and the stick is displaced by a very small amount from the central position to provide the necessary motor current from the servo amplifier. The servo loop has a relatively high gain or stiffness. Further increasing the stick force will result in the breakout force being reached, and continuing to the increase the stick force is matched by the appropriate motor force. The controller generates the appropriate stick displacement demand corresponding to this force, and the stick is driven by the servo motor, so that the displacement coincides with the demanded value. The output of the stick displacement sensors are majority voted and provide the pilot's command signal. For example, pitch rate and roll rate to the FBW computer. The integrity aspect need to be considered and the following elements examined. And first, mechanical integrity of the gear drives and gimbal bearing. The probability of a mechanical jam can be made very low, and in the unlikely event of a jam, the aircraft can be controlled by the force sensor output, typically duplex. Second, failures in the servo amplifiers and gimbal servo motor. The MTBF of a servo amplifier and motor combination is of the order of 4,000 hours, so that a duplex configuration meets the integrity requirement. The servo motors can have dual winding, with the one winding providing the means of control and the other winding providing standby control through a standby servo amplifier, so that only one servo motor per axis is required. In the unlikely event of loss of servo driver, the pilot can still move the stick and exercise a degree of control of the aircraft. Our next topics of this lecture, fly-by-light flight control. Mention has already been made of the common mode failures that can be caused by the severe electromechanical interference if the equipment is not effectively screened from electromechanical interference, EMI. Electromechanical interference can arise from lightning strike. In this case, very large electromechanical pulses with electrical field strengths of hundreds of volts per meter and can reproduce and a very wide spectrum of electromagnetic radiation frequencies generated. Overflying high-power radio or radar transmitters, several cases have occurred of aircraft experiences severe transients in the automatic flight control system, placing the aircraft temporarily out of control, whilst overflying high-power radar and radio transmitters. And this has been due to the susceptibility of the flight control system, analog electronics, to EMI because of inadequate electromechanical screening. Current digital flight control systems are designed to much higher electromagnetic compatibility, EMC specification. That is the ability to withstand high levels of EMI and should be able to withstand such environment. Failures in the electromagnetic screening system so that the avionic equipment becomes susceptible to internal source of electromagnetic radiation, such as radio and radar equipment, electrical generators, etc., or external sources of EMI. Failure of the electromagnetic screening can result from breaks or high resistance in the Earth's connections to the aircraft structure and the electrical bounding of the structure due to the corrosion, poor quality installation, and enough. Such failures can be of a dormant nature and might only become apparent when an abnormal EMI source is encountered. Vicinity to a nuclear explosion and consequent emission of gamma radiation and EMP of very high electric field strength. Military avionic equipment is specifically designed to survive up to a certain or classified level of these effects. This attribute is referred to as a nuclear hardness and is achieved by the design of the circuits, use of nuclear hard components, circumvention techniques, and very efficient electromagnetic screening. Subject is beyond the scope of our lecture, and much of the information on the subject is of highly classified nature. However, a military aircraft with a nuclear hand flight control system must have a very low susceptibility to EMI to meet the nuclear hardness specification. Electronic units and their enclosures or boxes can be designed to have very efficient electromagnetic screening. However, the Achilles heel of the system can be the Achilles heel of the system can be interconnecting cables which link together all the elements of the system. These interconnecting cables must have very efficient electromagnetic screening, which incurs a significant weight penalty. The incoming wires from the cable to these units or boxes must also be terminated with electromagnetic filters, which present a low impedance to EMI, induce transient voltages in the cable. The transient voltages are thus attenuated before they can affect the circuits inside the box. The use of digital data transmission enables error check and coding to be incorporated in the digital data word format so that any corruption of the digital data by EMI can be detected and the data ignored. However, the data are lost and the system frozen for the period of the interference, so that only a short transient loss would be tolerated. The integrity of the screening of the interconnecting cable must thus be very high indeed to meet the flight safety requirements. The use of optical data transmission, whereby digital or analog data is transmitted as a modulated light intensity signal along a fiber optic cable overcomes this problem. The optical transmission media is unaffected by EMI and very much higher data rates and can be achieved like gigahertz bandwidth, like 109 Hz in power 9. Current avionic data bus systems using fiber optic data transmission operate in the 20 to 100 megabits per second bracket. Okay, 1 second, please. I just want to break for a second due to my conditions. Please, sorry. Okay, let's continue our lecture. 1 second, please. So, the fiber optic cable is also much higher, much lighter than the equivalent screen cables it replaces. The weight saving can be significant, and as mentioned a bit earlier, weight saved on equipment installation is geared up by a factor of about 10 on the overall aircraft weight. A further driver of the adoption of optical data transmission is the extensive use of composite materials in the aircraft structure and the consequent loss of the screening provided by an aluminum skin, which forms a Faraday cage as far as external electric fields are concerned. The use of fabric optic links to interconnect the basic elements of the flight control system, pilot stick, sensor, flight control computers, actuator control electronics, has become known as a fly-by-wire flight control system. It should be noted, however, that while a number of prototype aircraft have flown with flight control systems using fiber optic links, there are no production aircraft in service with a fly-by-wire flight control system in mass production. At the time of you listening this lecture, maybe at the first time for this concrete day. And this is because electrical bus systems have proven entirely adequate and interconnection with the bus is relatively simple. Fiber optic connectors and passive couplers are not readily available and are still relatively expensive. Next subtopic today's lecture, fly-by-wire flight control system. A fly-by-wire flight control system configuration is shown schematically in this slide. The accompanying redundancy is omitted for clarity. The fiber optic links interconnecting the units of the flight control system eliminate the possibility of propagating electrical faults between units, as the optical fiber is an insulator. Fiber optic links can be bidirectional and can also be used to convey the system status to the pilot's control or display panel. For instance, a wraparound test can be carried out to check that the data have reached their destination and the status or health of the control surface actuation system can be checked by monitoring the servo error signal and actuator hydraulic pressure. The actuator control electronics and actuator are located in fairly close proximity to each other, and the only connections required there are the fiber optic cables and electric power supplies. The large wiring harness required in earlier analog systems being eliminated. Such systems are sometimes referred to as smart actuators. A further advantage of fiber optic data transmission is the ability to use wavelength division multiplexing, whereby a single fiber can be used to transmit several channels of information as coded light pulses of different wavelengths or colors simultaneously. The individual data channels are then recovered from the optically mixed data by passing the light signals through wavelength selective passive optical filters, which are tuned to the respective wavelengths. WDM has a very high integrity as the multiplex channels are effectively optically isolated. It is interesting to note that one of the first applications of fly-by-wire technology has been on the earliest flying vehicle, namely the airship. Non-rigid airships may be acquiring a new lease of life as long-duration platform for airborne radar surveillance systems. The airship is able to carry a large high-power radar antenna within its envelope and is able to remain airborne for several days, with occasional in-flight refueling while hovering over a supply chain. It can also carry the relatively large crew required for 24 hours operation in considerable comfort. Fully powered controls are required for the airship's large control surfaces because of the need for autopilot operation on long-duration missions and auto-stabilization to counter an inherent pitch instability and provide yaw damping. The long control cables required from the gondola to the control surfaces. It's about from 100 to 200 meters on the projected large airship. And the probability of experiencing lightning strikes make an optically signal flight control system an attractive solution. It is interesting to note that proof of concept Skyship 600 airship first flew with an optically signaled flight control system in October 1988, so many years ago. Next subtopic today is optical sensors. There are a large number of sensors involved in the flight control system for a representative civil and military aircraft, respectively. Many of these sensors being at quadruplex level. The approximate location of sensors is indicated, and it can be seen that many are located near the extremities of the aircraft and possibly less well screened than fuselage-mounted equipment. The extensive use of composites can further degrade electromagnetic screening in the vicinity of such sensors. The use of what are referred to as passive optical sensors offers particular advantages in such applications as these sensors are not affected by EMI. Passive optical sensors are defined as sensors which do not require electrical supplies or any electronic processing at the sensor. the output of the sensor being an optical signal, which is modulated by the quantity being measured. The processing of this optical signal is carried out by a separate electronic unit, which is fully screened from EMI. The only connection between the sensor and the electronic unit being an optical fiber cable. The basic concept of such sensor is shown in this slide. And now we have a next part of our lecture. Its main topic called inertial sensors and attitude derivation. So now we have a new part of our lecture. Gyroscopes, the abbreviation of gyros and accelerometers, are known as inertial sensors. And this is because they explore the property of inertia, namely the resistance to a change in momentum, to sense angular motion in the case of the gyro, and changes in linear motion in the case of the accelerometer. Okay? They are fundamental to the control and guidance of an aircraft. For example, in fly-by-wire aircraft, the rate gyros and accelerometers provide the aircraft motion feedback, which enables a maneuver command control to be achieved and an aerodynamically unstable aircraft to be stabilized by the flight control system. Gyros and accelerometers, gyros and accelerometers are also the essential elements of the spatial reference system, or attitude or heading reference systems, and the inertial navigation systems, INS. They largely determine the performance and accuracy of the systems and account for a major part of the system cost. The attitude heading reference system and inertial navigation system share common technology and operating principles. This part of our lecture covers gyros and accelerometers and attitude derivation from the strap-down gyros and accelerometers. It provides the basic background to inertial navigation and AHRS, attitude heading reference system. The accuracy requirements for gyros and accelerometers can differ by several orders of magnitude depending on the application. This table shows the accuracy requirements for a typical fly-by-wire flight control system and 1 nanometer per hour step-down INF, as representing the lower and upper end of the performance spectrum. Not surprisingly, the cost can also differ by an order of magnitude or more. The quest for an attainment of the accuracies required for inertial navigation have involved many billions of dollars expenditure worldwide, and the continual exploitation of state-of-the-art technology. For example, the world's first laser was demonstrated in 1960, and the first experimental ring laser gyro was demonstrated 3 years later, with an accuracy of a few degrees per hour. The first production of laser gyro-based inertial navigation system, which is required only 0.01 degrees per hour accuracy, and went into large-scale civil airline service in 1981. Strip-down RLG, ring laser gyro based IN systems, now determine the market, a technology revolution. The gyros used in all the designs of control and guidance systems are what is termed spinning rotor gyros, as they explore the angular momentum of a spinning rotor to sense angular motion. However, their mechanical complexity and inherent failure mode constrain their cost and reliability and hence cost of ownership. Power consumption and run-up time are further limiting parameters of this technology. High accuracy inertial navigation systems require the angular momentum gyros to be isolated from airframe angular motion because of their limited dynamic range. This is achieved by mounting them on a gimbal suspended stable platform. The reliability and cost of ownership of stable platform INF is thus inevitably limited by its complexity. Gyros operating on solid state principles and which can be body mounted, sometimes seen as a step down, and have thus been developed because of their intrinsically higher reliability and certainly lower cost of ownership. Optical gyros, such as the ring laser gyro, and more recently the fiber optic gyro, have displayed the spinning rotor gyro. At the lower end of the accuracy spectrum, micro-machined vibrating mass rate gyros exploiting semiconductor manufacturing technology have become well established. Avionic applications include flight control and solid-state standby artificial horizon. They are extremely reliable and rugged devices with low power consumption and offer the major advantage of relatively low. It is interesting to note that the name gyroscope is derived from the Greek word gyro, meaning rotation, and scoping, meaning to view, and is the name given by French physicist Jean Foucault to the gimbal-mounted spinning flywheel he used to measure the Earth's rotation in 1852, the world's first gyro. To view rotation is thus a good description of the function of all types of gyros. Another subtopic of today's lecture is named the Micro Electromechanical Systems MEMS Technology Rate Gyro. These gyros explore the effects of the Coriolis forces, which are experienced when a vibrating mass is subjected to a rate of rotation about an axis in the plane of vibration. There are two basic configurations which are being exploited: a tuning fork configuration and vibrating cylinder configuration. Second, please. Both configurations can explore micro-machining technology and integrating circuit manufacturing methods enable miniature, extremely robust sensors to be constructed which have no wearing parts in their mechanism, and with MTBF is excess of 100,000 hours. And very importantly, they can be of relatively low cost. This fabrication technology has been given by acronym MEMS, that is electromechanical system, in the US, and this sensor are MEMS sensors. They are being exploited not only in avionic applications, such as flight control, standby altitude, and hidden reference systems, and missile mid-course guidance, but also in the automobile industry in car stability enhancement systems. Other applications include robotics, factory automation, instrumentation, GPS augmentation for vehicle location systems, navigation systems, precise farming, antenna stabilization, camera stabilization, autonomous vehicle control. In short, there is a very large market for these array gyros, apart from aerospace application, and this drives the cost down. These developments in gyro fabrication technology have come into large-scale exploitation over the last decade and have had a revolutionary impact. For the first time, miniature solid-state array gyros with MTBF in excess of 100,000 hours became available at relatively low cost. Of course, are dependent on the accuracy requirement and the size of the order, but for a mass market application, such as the automobile industry, the cost must be of the order of 50 to 100 US dollars or less to be competitive in a very highly competitive market. It is interesting to know that nature has evolved such sensors over many million years in the common house fly, which uses vibrating halters to sense rate of rotation. The fly has been described as a control configured flying vehicle in its unsurpassed maneuverability, as anyone who has tried to spot a fly can confirm. The halters, the effectively small flexible rods with a mast at the end, and have evolved from a vestigial second pair of wings. Amputation of the halters results in unstable flight, just like the loss of the ray gyros in an aerodynamically unstable fly-by-wire aircraft. Because of space constraints, attention has been concentrated on the quartz tuning fork type of micro miniature ray gyros. This appears to be the most widely used type at the time of writing, but no disparagement is implied in any way of the vibrating cylinder type. The basic principle of the tuning fork ray gyro is briefly explained as from this slide. Refer to the left figure A, which shows a single vibrating key time. If the base is rotated about the x-axis, you can see it's vertical, while the mass is oscillating in the y direction, the Coriolis forces induced will cause oscillations to be built up along the z-axis directed to the left side, providing the elastic support is exactly symmetrical. Such oscillations will be in phase with the original y motion. The plane of oscillation tends to stay fixed in space. Such a simple instrument suffers from the unacceptable characteristic that the smallest linear motion applied to its base causes unacceptably large error. To overcome the effect of base motion, it is necessary to use balance oscillations, in which the oscillation of one mass are counterbalanced by equal and opposite motion of a second equal mass, as shown in the figure B on the right part of this slide. The amplitude of the torsional oscillation about the x-axis or input axis is directly proportional to the input rate. To obtain maximum sensitivity, the size and shape of the tuning fork stem is such that the torsional vibration frequency of the tuning fork about its axis of symmetry is identical to the flexural frequency of the tuning fork. This amplitude is measured by suitable sensors to given output signal proportional to input rate. And this figure outlines the basic theory. But you should note in here, Coriolis accelerations are discussed a bit further in the next slide. And this slide is show the gyro chip vibrating quartz unit 4 grade gyro developed by the BEI Systrom Donor Inertial Division. The author is indebted to the company for permission to publish this information. The basic configuration is shown schematically in this slide and comprises a vibrating quartz tuning fork to sense angular rate, which is coupled to a similar fork as a pickup to produce the rate output signal. The piezoelectric drive turns the driven by an oscillator to vibrate at a precise amplitude. An applied rotation rate about an axis parallel to the vibrating turns causes a sine wave of torque to be produced resulting from the Coriolis acceleration, as explained a bit earlier. Okay? And this oscillatory torque in tune causes the tunes of the pickup fork to move up and down, in and out of the plane of the fork assembly. And this causes an electrical output signal to be produced by the pickup amplifier, which is amplified and phase-sensitive rectified to provide a DC signal, which is directly proportional to the input rate. By the way, the sign of the DC output signal changes sign when the input rate reverses due to the action of the phase-sensitive rectifier. The pair of tuning forks and their support flexures and frames are batch fabricated from zinc wafers of single crystal piezoelectrical quartz and are micro-machined using photolithographic processes similar to those used to produce millions of digital quartz wristwatches each year. And this slide shows a fabrication wafer. Standard rate ranges from plus minus 50 degrees per second up to thousands degrees per second. Threshold resolution is less than 0.004 degrees per second. It means less than 50 degrees per hour, Earth's rate of rotation. And the bandwidth of 90% loss is greater than 60 Hz. Startup time is less than 1 second, and power consumption are less than 0.7 watt. Nonlinearity, no higher than 0.05% of full scale. To achieve the highest accuracy requires accurate modeling in the system computer of the temperature-dependent error. Several manufacturers use quartz tuning fork rate gyros for deriving the aircraft attitude in their solid-state standby display instruments, a good testimony to their performance and attribute of small size, low power consumption, very high reliability, and competitive cost. It should be noted that the tuning fork gyro is not a new concept, sorry. Meredith took out a patent for such a device in 1942 when he was working at the Royal Aircraft Establishment at Harvard. Further development was carried out in the late 1950s by Master Hunt and A. Hope, who demonstrated a performance of less than 1% per hour driven. It is micro-machining technology and semiconductor fabrication methods which have enabled the advances to be achieved. I hope you enjoyed this lecture, and I'm looking forward to see you next time to continue this lecture topic. Okay, bye.